Combinatorics Lecture 14, Generating Functions of Recursive Sequences. Let us make a quick recap. Assume that we have a sequence of complex numbers, ai, where I is greater than or equal to 0. Then the ordinary generating function of this sequence is the formal power series, which we denote by g, it depends on a, and the variable is x. And this formal power series is defined as a sum over all I greater than or equal to 0, ai times x to the power I. And we do not impose any conditions on convergence of this sequence. However, if the sequence does converge in some neighborhood of 0 to some nice function f of x, we can use this function f for computations related to our sequence. And today we will pay special attention to the case when our sequence A satisfies some recurrence. Let us recall the notion of a rational function. A rational function is a function that can be written in the form f of x divided by g of x, where f and g are two polynomials, of course with g different from 0. The constant polynomial 0. G is a polynomial which might have some zeros, but we assume that it is not equal to the polynomial which is constant and takes 0 values at all points x. Two rational functions f divided by g and f tilde divided by g tilde are equal if and only if f times g tilde is equal to g times f tilde, now as polynomials. And the set of all rational functions is denoted by c of x with this kind of brackets. This set is a field with respect to the usual addition and multiplication of functions. We remark that each non-zero rational function admits a unique presentation in the form f of x divided by g of x, where the greatest common divisor of f and g is 1, and the leading coefficient of g is equal to 1. We can call such an expression the reduced form of the rational function. Now we can formulate our main theorem. Let A be a sequence of complex numbers, so I greater than or equal to 0. Then there exists a positive integer k and complex numbers gamma 1, gamma 2, and so on gamma k, such that an is equal to gamma 1 an minus 1 plus gamma 2 an minus 2 plus and so on, plus gamma k an minus k for all n greater than or equal to k, if and only if the generating function for a is a rational function f of x divided by g of x, where g of 0 is equal to 1, so the free term of g is equal to 1. And this condition that g of 0 is equal to 1 is very essential for the whole theorem. Proof. Assume first that our sequence A is constant recursive, so there exists k greater 0 and gamma 1 and so on gamma k complex numbers, such that an is equal to gamma 1 an minus 1 plus and so on plus gamma k an minus k for all n greater than or equal to k. Consider the characteristic polynomial of this recursion. We denote it by chi of x, and it is equal to x to the power k minus gamma 1 x to the power k minus 1 minus and so on minus gamma k. Define the polynomial g of x as x to the power k times chi evaluated at 1 divided by x. Explicitly, this is a polynomial 1 minus gamma 1x minus gamma 2x squared minus and so on minus gamma k x to the power k. Note that g evaluated at 0 for this polynomial g is equal to 1 by definition. Now we claim that multiplying the generating function for a with our polynomial g of x outputs a polynomial of degree at most k. Indeed, if n is greater than k, then the coefficient at x to the power n in this product, the generating function times g of x, equals an minus gamma 1 an minus 1 coming from here, minus gamma 2 an minus 2, and so on, minus gamma k an minus k coming from here. And this is equal to 0 due to our recurrence. And this means exactly that f of x, defined as the generating functions times g of x, is a polynomial. which of course implies that the generating function is a rational function. It can be written as f of x divided by g of x, where f and g are polynomials, and the value of g at 0 is 1. Let us now prove the converse implication. Assume that the generating function can be written in the form f of x divided by g of x, where f and g are polynomials and g of 0 is equal to 1. Then, of course, the generating function times g of x is equal to f of x. This means that if n is greater than the degree of f, then the coefficient at x to the power n in our product, the generating functions times g, must be 0. If we assume that g of x is the following polynomial, 1 minus gamma 1x minus gamma 2x squared minus and so on, minus gamma k x to the power k, which we can assume because the value of g at 0 is 1, so this is fixed, and then gamma 1 and so on, gamma k are some numbers. Then, for any n which is greater than or equal to the degree of g, which we assume is equal to k, the coefficient at x to the power n in our product of the generating function times g is an minus gamma 1 an minus 1 minus and so on minus gamma k an minus k. But this means that if n is greater than the maximum of the degrees of f, or the degree of g minus 1, then an minus gamma 1 an minus 1 minus and so on minus gamma k an minus k is equal to 0. And that's exactly what we wanted to prove. This gives us our recurrence. And of course, in the second part of the proof, the characteristic polynomial of the recurrence which we have is exactly x to the power degree of g times g evaluated at 1 divided by x. Here is an example. Let us consider the sequence of Fibonacci numbers fn, which is defined as f0 is equal to 0, f1 is equal to 1, and fn is equal to fn minus 1 plus fn minus 2 for all n greater than or equal to 2. Then, directly from this recurrence, we have that if we take the generating function for this sequence, then subtract x times the generating function, and then subtract x squared times the generating function, we get the polynomial. And it is very easy to check which polynomial will we get. We will get the polynomial f0 plus f1x, it comes from this summand, minus f0x from this summand, and this summand will contribute to nothing. But the same polynomial is equal to 0 plus x, so this is equal to x. And this implies that the generating function for the Fibonacci sequence is the rational function x divided by 1 minus x squared. Moreover, for arbitrary f0 and f1, if we don't take the specific values 0 and 1, which we have in the classical Fibonacci sequence, if we take f0 and f1 as parameters, then we get a sequence with the following generating function. The numerator of the rational function will be f0 plus f1 minus f0 times x, and the denominator will be 1 minus x squared. Now, how can we use this generating function for the Fibonacci sequence? We can use it to give an alternative description of the explicit formula for the general term of the sequence. Indeed, the polynomial 1 minus x squared, which appears in the denominator, can be factored into a product of two linear factors. We can write that 1 minus x squared is equal to 1 minus 1 plus the square root of 5 divided by 2 times x times 1 minus the square root of 5 divided by 2 times x. When we can factor the denominator in the product of such linear factors which are different, we can rewrite our fraction as a linear combination of two fractions with smaller denominators. So we can write our x divided by 1 minus x squared as the fraction with the numerator 1 divided by the square root of 5, and the denominator our first factor, 1 minus 1 plus the square root of 5 divided by 2 times x. and then minus the second fraction, the same numerator, 1 divided by the square root of 5, and the denominator is the second factor, 1 minus the square root of 5 divided by 2 times x. Now we can use the formula for the geometric series to rewrite the first summand in the following way. So 1 divided by the square root of 5, that's just the scalar factor which comes from the numerator, times the sum over all n greater than or equal to 0, and then we should take this term to the power n. So 1 plus the square root of 5 divided by 2 to the power n times x to the power n. Similarly, we can rewrite the second summand. So we have the scalar factor 1 divided by the square root of 5, sum over all n greater than or equal to 0, and then this element to the power n. So 1 minus the square root of 5 divided by 2 to the power n times x to the power n. And now, since our generating function is the difference between these two series, we get that the coefficient at x to the power n, which is exactly fn, is equal to 1 divided by the square root of 5, that's a common scalar factor, and then we should take the difference between the corresponding coefficients at x to the power n. This gives us 1 plus the square root of 5 divided by 2 to the power n minus 1 minus the square root of 5 divided by 2 to the power n. And this is our usual expression for fn. We can get the same expression by a different method. Recall that the coefficient at x to the power n in the expression for the generating function can be obtained as 1 divided by n factorial times the evaluation of the nth derivative of the generating function at x is equal to 0. Let us look at the nth derivative of the first summand. 1 divided by the square root of 5, we can just take it out, so 1 divided by 1 minus, and then this expression 1 plus the square root of 5 divided by 2 times x. When we take the nth derivative of this expression, we will get our factor 1 divided by the square root of 5, and then the coefficient at x will be to the power n, and then we times n factorial because any derivation will increase the power in the denominator, and then the denominator will be to the power n plus 1. And similarly for the second summand, the only difference is that the coefficient at x is different. We have minus the square root of 5 compared to plus the square root of 5 in the first summand. Otherwise they look exactly the same. And now when we evaluate x to 0, the denominator becomes 1, so we can forget it. And we have to divide by n factorial, which kills this n factorial in the numerator. What remains is the usual expression for fn, 1 divided by the square root of 5 times the difference between 1 plus the square root of 5 divided by 2 to the power n and 1 minus the square root of 5 divided by 2 to the power n. So now we have computed this expression for fn in 3 different ways, and in 2 different ways using the generating functions. Recall that we looked in one of our lectures at the sequence of Catalan numbers. Recall how it is defined. So we have the Catalan number Cn, where n is greater than or equal to 0, and Cn is defined as the number of grid walks from the point 0, 0 to the point nn, where each step is either 1, 0 or 0, 1, and the walk should satisfy the condition that it stays weakly below the main diagonal x is equal to y. And we know that Cn is equal to 1 divided by n plus 1 times 2n choose n. First of all, we claim that the sequence Cn satisfies the following recurrence. C0 is equal to 1, which is obvious, and then Cn is equal to C0 times Cn minus 1 plus C1 times Cn minus 2 plus and so on, plus Cn minus 1 times C0 for all n greater than 0. So here is an example. The Catalan sequence starts 1, 1, 2, 5, 14, 42, and so on. So and we have that the second one is equal to 1 times 1. 2 is equal to 1 times 1 plus 1 times 1. 5 is equal to 1 times 2 plus 1 times 1 plus 2 times 1. 14 is equal to 1 times 5 plus 1 times 2 plus 2 times 1 plus 5 times 1, and so on. So we can check that this is okay for a few starting terms of our sequence. So let us prove this claim. So assume that n is greater than 0, and let us denote by omega the set of all grid walks which are enumerated by Catalan numbers. So these are walks from 0, 0 to nn, with steps 1, 0 or 0, 1, and these walks stay weakly below the main diagonal. For k between 1 and n, let us denote by omega k the set of all elements in omega which pass through the point k, k, but not through any point I, where I is between 0 and k. Then, of course, directly from the definition, omega is equal to the union over all k from 1 to n of omega k's, and these omega k's are disjoint. So by the rule of sum, the cardinality of omega is equal to the sum over all k from 1 to n, the cardinality of omega k. Let us now examine each omega k in more detail. Any walk in omega k consists of two independent parts. First of all, we have a walk from 0, 0 to k, which never visits the main diagonal apart from the first and the last point. And then we have a walk from kk to nn, which stays weakly below the diagonal. So by the definition of the Catalan numbers, the second part is enumerated by c with the index n minus k. If we look at the first part, a walk from 0, 0 to kk, it never visits the main diagonal, and so we can look at its piece, which starts from the point 1, 0 after the first step, and finishes at the point k, k minus 1, so that's the penultimate step. Then this walk must weakly stay below the subdiagonal given by the equation x is equal to y plus 1. Therefore, the first part must be enumerated by c with the index k minus 1. The parts are independent, so by the rule of product we get that the cardinality of omega k is equal to ck minus 1 times cn minus k. And this implies immediately our recurrence, that cn is equal to c0 cn minus 1 plus c1 times cn minus 2 plus and so on, plus cn minus 1 times c0. So here is the illustration of this proof. So this is 0, 0, this is nn, and the Catalan walks are walks in this triangle. So we can weakly visit the main diagonal, but we cannot cross over. However, so assume that we have here kk, so our first part of the path goes from 0, 0 to kk and never visits the main diagonal. So in this part we have this smaller triangle, which we can interpret as a walk from 0, 0 to k minus 1, which stays weakly below the main diagonal. So this is our ck minus 1. And from the point kk to nn, we have this triangle. This is exactly cn minus k, the Catalan walks in this triangle. So this is how we can illustrate our proof on a picture. Now let us use this recurrence to compute the generating function for Catalan numbers. So the generating function gcx. Let us observe that if we multiply this generating function with itself, the outcome will be the sum over all n, and then for a particular n, the coefficient at x to the power n will be the sum over all I between 0 and n, ci times cn minus I. But this gives exactly cn plus 1 due to our recurrence. So the product of the generating function with itself outputs the sum over all n, cn plus 1 times x to the power n. If we multiply this with x and add c0, we get our generating function back, which means that our generating function satisfies the following equation. The square of the generating function equals the generating function minus c0, which is just 1, divided by x. Or in other words, our generating function satisfies the quadratic equation x y squared minus y, plus 1 is equal to 0 with respect to the unknown y. Of course, we can solve the quadratic equation in y. So with respect to y, the solutions to this quadratic equation are 1 plus minus the square root of 1 minus 4x divided by 2x. So, of course, we want our generating function to work for all n, and we know that c0 is equal to 1. So we need that our generating function has value 1 when x is 0. Now we have here a fraction where we have x in the denominator. This means that we should be talking about the limit of this function when x approaches 0. If we take the positive sign 1 plus the square root, this is not bounded when x approaches 0, so this cannot be the right answer. While if we take the minus sign, then 1 minus the square root of 1 minus 4x divided by 2x, this tends to 1 when x approaches 0. We can use the L'Hopital's rule to we take derivative of both numerator and denominator, and we get 2 in both cases. So we deduce that the limit is equal to 1. So we can now conclude that the generating function for the Catalan sequence is the function 1 minus the square root of 1 minus 4x divided by 2x. So that's the generating function for the Catalan sequence. Note that this is not a rational function because what we have here in the numerator is not a polynomial, we have some square root here. Let us compute one more example of how one can get a generating function for a sequence which satisfies some recurrence, in this case a non-homogeneous recurrence. So let us compute the generating function for the sequence A, which is given by the recurrence a0 is equal to 0, and an is equal to an minus 1 plus 1, for each n greater than 0. Of course, the sequence which is behind here is an is equal to n. The identical sequence. Consider the generating function for our sequence. Directly from the recurrence which we have, we get that the sum over all n, an plus 1 times x to the power n plus 1 is equal to the sum over all n, an times x to the power n plus 1 plus the sum over all n, x to the power n plus 1. Now, if we use the formula for the sum of the geometric series, we get, so here on the left-hand side we have our generating function minus a0, but a0 was 0, so this is our generating function. The first summand here is x times the generating function, and the second summand is just the geometric series, so it's equal to x divided by 1 minus x. So we move the first summand to the left-hand side, we have 1 minus x times the generating function, and so the generating function equals x divided by 1 minus x squared. So this is the generating function for our sequence. Note that this is a rational function, so this sequence can be described by a homogeneous recurrence, which we actually know, but we also know that that recurrence should have degree 2 and not degree 1, where we have the non-homogeneous recurrence of degree 1. Some additional problems and questions at the end. Problem question 1. Prove with all details that c of x is a field, that rational functions form a field. Problem question 2. Find a closed formula for the general term of the sequence with generating function 1 minus x divided by 1 minus x plus x squared. Problem question 3. Compute the generating function for the sequence n times cn, the Catalan number, for n greater than or equal to 0. Problem question 4. Prove the following identity for Catalan numbers in two different ways, using the combinatorial arguments like bijective proof and then using the generating functions. So the identity is that the middle binomial coefficient to n choose n is equal to the sum over all k from 0 to n, and then the Catalan number Cn times the middle binomial coefficient 2 times n minus k, choose n minus k. And problem question 5, determine the generating function for the sequence B, given by the recurrence b0 is equal to 0, and bn is equal to bn minus 1 plus n for all n greater than 0. Thank you very much, and see you next time.